Okay, so this is going to be the last revision video, and it is going to be on experimental design. I'm going to cover the last 4 dot points of the chemistry checklist, and I'm going to talk about these using an example of an experiment that you can design. So essentially, we're going to look at an experiment relating to reaction rate and collision theory and factors affecting reaction rate. So this is an experiment. I want to determine the effect of concentration on reaction rate. Now, in order to design this experiment, and those of you who were in class last term, you actually did this in class. I have to give you a reaction first, and we're going to do the one that we actually did in class last term, which is between the reaction between magnesium and hydrochloric acid. So you add the piece of magnesium into a solution of hydrochloric acid, and you will produce some hydrogen gas. The magnesium is going to dissolve in the acid, and then you can use this hydrogen gas as a way to measure reaction rate. So this is the reaction. Once again, the purpose of the experiment is to determine the effect of concentration on reaction rate, which means that the independent variable in this case is going to be concentration, and it's going to be concentration of the acid because the acid is actually a solution here. If you look at the state, I can't really vary the concentration of magnesium because it's a piece of solid. So let's say I have two different concentration, and some of you did this. You do 1.0 molar and 2.0 molar. That will be the independent variable. The dependent variable in this case is going to be reaction rate because that's what you're trying to measure the effect of. No, you're not measuring the effect of reaction rate. You're measuring the effect on. Okay, so there are two ways generally to determine reaction rate. But regardless of which ways that you use, you have to understand that it is a measure of speed. So you're trying to work out how fast the reaction is happening. That's why it's called reaction rate. So you can either measure the speed at which the reactants are being consumed over time, or you can measure the speed at which the products are being produced over time. So it really depends on the availability of equipment and the state of the reactants and products. You can choose which method you would use to estimate reaction rate. Now, the unique thing about this experiment and this particular chemical reaction is that one of the products is a gas. So you can collect the gas over time and use that as a way to measure reaction rate. So I'm going to probably focus on the second one, which is to measure the speed at which the products are being produced over time. So let's talk about different methods to measuring the product being produced over time. I think this is the one that a lot of you used in class when we did this designing the experiment, and you just put the magnesium and the hydrochloric acid. So in the conical flask here, so you have magnesium and you have HCl, and then you very quickly cover the top of the conical flask with a balloon, and then you can collect. So any hydrogen gas that is produced is going to go into the balloon. Now, if you really want to use this setup to measure reaction rate, then you have to make sure that you measure the width or the diameter of the balloon, perhaps every 15 seconds. So you don't want to wait until the end to measure, but you want to measure how fast the balloon is being inflated. I think I showed you this setup, but we didn't do it, which is to use a gas syringe. So this is a more precise and complicated setup, and you get to do this if you stick with chemistry until year 12. So essentially, it's the same thing, but instead of collecting the gas into a balloon, you collect it into a gas syringe, so you can very correctly, accurately read the measurement on the syringe to know exactly what volume of gas is being produced over time. I cannot remember whether I did actually show you this setup, but this is another alternative. So essentially what you do is you can measure the decrease in mass of the reaction mixture over time, because as you add the magnesium and the hydrochloric acid, and if the gas escape, there will be a decrease in the mass of the conical flask and the content, and that's a way to determine reaction rate. But in this case, you're measuring the rate of reactants being consumed over time. So I think the method that we're going to focus on is going to be this method, because that's the one that we actually did in class. So let's recap. The independent variable is the concentration of hydrochloric acid. The dependent variable is reaction rate as measured by the change in diameter of the balloon over time. So In this case, I'm being very, very specific in terms of what exactly I am measuring, because you have to do that when you state the dependent variable. Now, the other things I want to point out is if this is a dependent variable, this is the independent variable, then everything else has to be controlled. So you need to use the same amount of magnesium, obviously. You need to use the same size of magnesium pieces. If you remember when we did this experiment, we had either magnesium ribbons, so you have like the long strips of magnesium, or you have the turnings with they're really small. So you can't vary the size of magnesium pieces. You have to stick to one. Otherwise, you're varying something else beside concentration. The volume of acid that you're using should be the same. The reason why you want these to be the same is because you want to produce the same volume of H2 overall. So the idea here is I'm not changing the amount of hydrogen gas that is produced from the reaction. I'm just changing how fast the production happens. So I just want to know whether it takes a longer period of time to get to the same volume of hydrogen gas. So eventually, if you have two different concentration of acid, eventually they have to produce the same amount of hydrogen. So eventually the diameter of the balloon will be the same. It's just how long does it take for each concentration mixture to get there. That's the only thing that you're measuring here. So you should not have different amount of hydrogen gas being produced later on when you measure the result. The size and type of the conical flask has to be the same. If you use two different types of conical flask, that could affect the rate of the reaction. Same for the balloon. And you want to make sure that you're measuring at the same time intervals, say every 10 seconds or every 15 seconds or something like that. And obviously the condition in the room should be kept constant, but these are the main controlled variables. Okay, so you have the independent variable, you have the dependent variables, everything else is controlled. The question is whether you use a lie graph or a bar graph. And essentially you're using a lie graph in this case because the variables are numerical and continuous. You're measuring change in diameter over time. So you're not going to use a bar graph because you should be able to connect the dots between say 15 seconds and 30 seconds. So that's why you're using a lie graph. And I just want to show you what it's going to look like if you need to represent the data. So let's say I will have one set of data for 1.0 molar, and it's going to be maybe in the form of a table of diameter of the balloon over, actually let's do time, diameter. So you have to start at 0, 0, and then maybe in 15 seconds. It really depends on what the reaction mixture is, but I don't know, maybe 10 centimeter, and then so on and so forth. So when you draw the graph, time will be the horizontal axis and the diameter will be the vertical axis. And you probably, what you're going to see is it's going to increase. And then at one point, it's going to stop increasing. So when you get to this point, essentially what happened here is all of the hydrogen has been produced and the balloon stopped getting bigger. So this is when all gas, or H2 gas, is produced. Okay, so your graph is actually the change in diameter over time, and this is going to be for 1.0, this is 1.0 molar. And if you want to see the effect of the difference in concentration between 1.0 and 2.0 molar, you would have to do another graph on the same set of scale for 2.0 molar. So when you do the experiment, you would collect the same type of data between time and diameter. So let's say that 0, 0, but at 15 seconds, maybe you already have 15 centimeters, something like that, and obviously keep going. So if I draw this on the same set of scale, maybe this is something that, okay. This is something that you can see. So this is going to be 2.0 molar. So notice how it gets to this point faster. So you look at this. So it takes less time to produce H2 gas. So it takes less time to produce a gas, but it has to produce the same amount because, as I just mentioned earlier, you're only measuring in this experiment the rate of reaction. You're not changing the overall amount of product. So both produces, and the reason why you're still producing the same amount of hydrogen gas is because you're using the same amount of magnesium. So changing the concentration of the acid is not enough to change the amount of product. So both of these will produce the same amount of gas, of H2 gas. Okay, so that's it. If this is your result, you should be able to conclude, oh, so the 2.0 molar reaction mixture has a faster reaction rate because it takes less time to produce the same amount of product, or the slope of this graph, the gradient of this graph is steeper than this one, and then you can use it to respond to your hypothesis. So that's all.